When a 6-ton bull elephant collapses for the final time on the African savanna, it creates an immediate biological anomaly. Thousands of pounds of calories, water, and minerals have suddenly materialized in a landscape where those exact resources are aggressively scarce. Biologists have long documented this phenomenon in the deep sea. When a whale dies and sinks into the dark, barren ocean, its immense body creates an isolated micro-ecosystem known as a whale fall, an oasis of food that sustains specialized deep-water creatures for decades. This diagram shows exactly how that marine concept maps onto dry land. Though smaller than a 40-ton whale, a 6-ton elephant generates the exact same radiating zones of scavenger activity, triggering what researchers call a terrestrial megafauna fall. Looking at the breakdown of this newly available biomass, the sheer volume is staggering. Out of 6 total tons, scavengers now have access to roughly 3 tons of dense muscle, thousands of pounds of organs and fat, and a massive skeletal structure laced with calcium. This sudden deposit of calories starts a biological clock. What follows is a highly structured, time-sensitive race between specialized creatures to dismantle the giant and reclaim its energy. Within 24 hours, the African sun accelerates the decay process, sending a concentrated scent plume across the plains. This summons the first wave of responders, the apex predators. Lions, leopards, and crocodiles zero in on the site. But these large predators face a physical obstacle. An elephant's skin is over an inch thick in places, woven with dense connective tissue that acts as a protective barrier. To bypass this armor, the predators target the softer, thinner tissues, usually around the eyes, trunk, and underbelly. By tearing through these specific points, they expose the dense layers of muscle underneath for the first time. Around day 3, the hierarchy shifts. Packs of spotted hyenas arrive in the dark. Using their overwhelming numbers and sheer aggression, they swarm the carcass, pushing out the lions and leopards to claim the exposed meat. This chaotic feeding is the first step in the breakdown. These top predators strip back the heavy hide, making the internal organs and deep tissue accessible to a much more specialized crew of cleaners. As the mammalian predators retreat, the sky fills with the next wave. Thousands of vultures, drawn from a 50-mile radius, descend on the carcass to strip whatever meat remains. This schematic reveals how these birds avoid competing with one another through a strategy called niche partitioning. Instead of fighting over the same scraps, different vulture species have evolved unique anatomical tools to divide the carcass into 3 distinct work zones. For example, the lappet-faced vulture wields a heavy, robust beak. They target the tough outer hide and thick tendons that the hyenas left behind, applying immense shearing force to tear the rigid material. Meanwhile, the white-backed vulture uses a long, slender neck and narrow beak to bypass the hide. They reach deep inside the exposed ribs to extract soft tissues from the internal cavities. These specific feeding strategies are backed by an extreme internal adaptation. Vulture stomach acid has a pH level near 0, making it highly corrosive. As the meat rots in the sun, it incubates pathogens like anthrax, botulism, and cholera. When the vultures ingest this infected tissue, their highly acidic digestive tract neutralizes the bacteria. Without this avian hazmat team, the rotting megafauna would become a massive biohazard, seeping disease across the ecosystem and infecting the local water supply. By the 30-day mark, the vultures have picked the frame clean. The ecosystem now enters the enrichment opportunist stage, passing control to millions of micro-scavengers. The skeleton is overrun by an invertebrate army. Swarms of hide beetles, blowflies, and flesh flies cover the remains, meticulously scraping away the final microscopic scraps of dried tissue and cartilage. This bleached ribcage provides a protected nursery. The insects lay millions of eggs inside the porous bone and skull cavities, fueling a population boom for the local food web. Simultaneously, a massive chemical transfer begins in the soil directly beneath the bones. This subterranean cross-section shows gallons of moisture and organic matter leaching from the remains. A concentrated plume of nitrogen and phosphorus embeds directly into the dirt, hyper-fertilizing the root systems. While the visible scavenging is ending, the chemical transformation of the savanna is now accelerating. 6 months later, seasonal rains hit the plains. The water batters the bleached bones, accelerating the final stages of physical decay. As the rain pools around the skeleton, it dissolves calcium and phosphorus out of the decaying ivory and bone, washing those raw minerals directly into the surrounding soil. This targeted injection of minerals creates a highly localized phenomenon known as a Carcass patch. This heat map tracks the soil fertility across the savanna. While the surrounding area remains nutrient-poor in blue, a massive spike of red and orange concentrates exactly where the elephant decayed. Switching this data to a direct comparison, we see the botanical result. The grass growing directly over the Carcass patch is taller, denser, and holds significantly higher levels of nitrogen and phosphorus than the standard savanna grass just a few feet away. The physical body of the 6-ton elephant has been dismantled, and its chemical makeup has been successfully converted into botanical energy. Around the 1-year mark, a new herd of elephants migrates across the plains, guided by memory and scent to the areas with the richest vegetation. They stop to feed directly over the site of the old bull. As a young calf grazes, tearing up the Carcass patch grass alongside a weathered, snapped tusk, biology comes full circle. The calf is actively absorbing the exact calcium, nitrogen, and phosphorus that built the old bull's skeleton. Over the span of 12 months, 6 tons of biological material sustained apex predators, fed thousands of vultures, fueled an insect boom, and hyper-fertilized the soil to grow the next season of grass. The death of a megafauna is a perfectly efficient system. It is the mechanism nature uses to redistribute a giant stored energy, passing it forward to sustain the generations that follow.